Hi, if you are looking for some thoughts, some concepts, some explanations about inductive logic or probabilities or Bayesianism, well, I'd like to invite you to watch this video, okay? My name is Salvador Gomes. I'm a master's degree student at the Federal University of Santa Catarina in Brazil. And I've made this video after my presentation on 13th Principia International Symposium that took place here in Brazil. Well, I hope you like it, okay? The idea is to share some thoughts about the coherence and the incoherence in Haeckel's inductive logic. I think it would be good to explain why I chose this book, the Professor Haeckel's works, as main reference to my presentation. Okay, Professor Haeckel has some books on the field, and I think this one is quite objective. It has a lot of practical examples. It brings many references to authors who wrote on the field. In fact, I really recommend this book, especially if you're looking for a text to start on the field, okay? But there is another reason that why I'm making this video and why I'm speaking about Professor Haeckel. This presentation is a kind of tribute to him who recently passed away. It was just a few months ago in May 10th. Okay, so thank you, Professor. As you can see in the title of his book, An Introduction to Probability and Inductive Logic, we are going to talk about probabilities. And you will start at the point where the theory had started. Paying attention to some gambling games. We are going to see two examples of betting in order to clarify what coherence in inductive logic is. Okay, let's see the first one. The number of people on 13 Principia, the event that we have already mentioned. Okay, let's say we know nothing about this number. Okay, and let's say that the letter n represents the assumption that the number of people in the symposium is an odd number. Let's bet. You bet $5 on n, on this assumption, and $6 on no n, or against n, okay? Your bookmaker, the bookmaker is a person who sets a betting contract, could be the house in a casino, for example. So your bookmaker offers $3 on n and $2 on no n, or against n. The stake is $8. The stake is the total price. Who wins the bet takes the stake, okay? Let's say that you accept this betting contract. Let's see what your payoff table shows, okay? What happens is if the result is n. In other words, what happens is the number of people in the symposium is an odd number, okay? Well, you receive the stake, but because you had bet $5 on n, your profit in this case is $3, okay? $8 from stake minus $5, $3. But you also had bet on no n, so you lose this money, okay? The result is minus $3 as your payoff, okay? But how about no n? What happens if the number of people in the symposium is an even number, okay? Well, you lose $5, the money that you had bet on n, but we receive $3 from the bookmaker, Once again, your payoff is minus $3. So no matter what in this situation, we are going to lose after all, and it's called sure loss contract or Dutch book, okay? According to Professor Hacking, this expression, Dutch book, was first mentioned by the British mathematician Frank Heinz, but no one has any clue why he named the situation that way. You know, it doesn't seem fair with people from Netherlands. Okay, moreover, Sherlock's contract is much more informative. But why? Why did this bet become bad news for you? Uh, the answer is because you had been incoherent on your bearing rates. Let's pay attention to the following table, okay? You bet $5 on N and the stake is $8. It means that your bearing rate in this case is 5/8 or 62.5% of the total stake. Okay, this number represents what the American mathematician Leonard Savage called a personal probability. Sometimes it's called a subjective probability or belief type probability, as Professor Hacking does in order to avoid a misleading idea. Because this number is not just a matter of opinion, it can be shared, it can be analyzed, is not just subjective, But let's move on. How about no N? You bet $6 on no N, and the stake is also $8. In this case, your bearing rate is 6/8, or 3/4, or 75% of the total stake. But we know for a fact that the number of people in this symposium in a room must be an odd number or an even number. It can be both. So in this case, we can add this number up, okay? But if you do that, the result is 11/8 or 137.5%. That means that you believe more than 100% in the results, okay? And it's not possible. In fact, it's a case of normality rule violation in the probability theory, okay? Let's see some rules. The first one, normality. This law says that the probability must be a number between 0 and 1, including them, okay? Like this formula shows. The second law, certainty. The probability of something certain is 1 or 100%, okay? Third law, additivity. For two mutually exclusive events, the probability of one or the other is the sum of the probabilities of each, like the formula suggests. And two mutually exclusive events are those ones like the numbers that we have already seen. If a number, if there is a number, it must be a odd number or an even number. Okay. So these laws are simplifications of the standard axioms of the probability theory, like those ones that were published by the Russian mathematician Andrei Kolmogorov in 1933. Okay, and these laws take some things for granted. They are for finite groups. We can use some logical connectives like or and. We can use the negation as well. For two logically equivalent proposition, the probabilities are the same, okay? And the deductive logic is taken for granted too. Now let's see the second example and complicate the things just a little bit, okay? At this point, who has already slept? Let's say the letter U represents the assumption that the most people here are understanding the idea, okay? And let's say the letter S represents the assumption that the most people here had taken a nap at least once since the beginning of this video, okay? Well, let's bet. Let's say that you have serious doubt if that it could be possible to get the idea here and take a nap at the same time. So you bet low on the assumption U and S, let's say 8%, okay? Uh, how about U and no S? Or in other words, the most people here are understanding the idea and the most people here hadn't taken a nap at least once. Well, we were not sure about, you decided to bet 15% on this one, okay? On the other hand, let's say that you're quite sure that just a few people here are getting the idea and most people here really had taken a nap at least once. So you go crazy, you bet 80% on this one. And how about no U and no S? The most people here aren't understanding the idea, and the most people here hadn't taken nap at least once. You don't believe in that, but you have doubts about it. So you decide 40% on this one, okay? Well, in a quick look, um, it it seems that there is no problem about with your bearing heights, or your belief type probabilities, if you will. They look reasonable, but how about U or S? How about the probability of this proposition? Well, this proposition is logically equivalent to no U and S. So they have the same probability, 8%. And no U and no S is logically equivalent to no U or S. So they have the same probability too, 40%. But this proposition on the right are mutually exclusive. It stands for that we can add the nap, you know. But if you do that, you're gonna see where the problem is. The result is 120%, and it's not possible. In fact, we are facing another case of sure loss contract, another case of normality rule violation. And pay attention, there is no interference from a bookmark. You just have been incoherent by yourself. Okay? Uh, but why is it important? Okay, let's see this three-step argument. We know now that coherence in inductive logic is to avoid a sure loss contract, okay? And avoiding a sure loss contract is to satisfy the basic laws of probability. And due to the fact that we are obeying the basic laws of probability, we can use the Bayes rule here. But what is Bayes rule? Well, Bayes rule was created by Reverend Thomas Bayes in 18th century. It's a kind of shortcut to solve math problems involving conditional frequency type probabilities. A frequency type probability is the one that you or we can exactly measure, as statistics. For instance, we can count the number of people who are watching this video, and we also can count the number of people among them who are Brazilians. Then we can express this relation by a fraction or a probability. I don't know, like 10%. Okay. Bayes' work can be represented by formulas like these on the screen, these bars between letters stand for given that. So we can say probability of H given that E, or since E is the case, the probability of each is ta 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 ta. But these letters weren't chosen by chance, they represent hypothesis and evidence. So we can hit this formula like this way. The probability of the hypothesis given that the evidence is probability of the evidence given that the hypothesis multiplied by probability of the hypothesis itself, and all the term is divided by probability of evidence itself. Okay, Bayes' rule is widely used in many areas of knowledge, such as computer science, financial, economics, biology, and so on. This approach is called Bayesianism. But what kind of problem can this rule solve? Let's see. With another example, you take an exam. Okay, are you actually sick? Let's say you go to the doctor and get tested for a rare disease. The exam indicates that you are sick. The test's accuracy is 96%, pretty high, says the doctor. Okay, we can represent the situation with this picture. Okay, probability of E given that age, or probability of the evidence. The evidence here is the test's positive result. Given that the hypothesis here is that you are sick, is equal 96%. Okay, if you will, you can think of these balls as being a box. Okay, you pick one up, and if it's a green one, the test is correct. Okay, the exam is correct. Okay. Well, it seems that you are sick. You have this uncommon disease. Let's see. Uh, Remember, the disease is rare, okay? Only 1% of people are actually sick. It means that in a group of 100 people, for everyone who has the disease, there are 4 false positives. So even though your exam had been positive, you are in a group of 5 people where only one is actually sick. It's a 1 in 5 or 20% chance. See the formula. Probability of age, probability of the hypothesis that you are sick, given that one evidence, one positive result is 1/5 or 20%. If you will, we can think of the balls as being in a box once again, and you are sick just if you pick the purple one up. No? Well, at first, the probabilities were tricky because we had ignored the base rate or the prior probability of this disease among the population. And that was what Bayes had been concerned about, the base rate, the prior probability about it. But let's move on. Let's say that you ask your doctor to take another exam. Does anything change? Well, now you are in a group of 100 people that 20 of them are sick. You take another test. Once again, the result is positive. How about your chances now? Well, the test's accuracy doesn't change because the exams are independent, okay? So in a group of 100, it can expect 4 false positives as well. But now you belong to a group of 24 people where 20 have the disease, okay? It's a 20 in 24, or about 83% chance. See the formula. Probability of age, probability of the hypothesis that you are sick, given that two positive results is 20/24, or about 83%. Okay, you are sick if you pick a purple ball up from the box. Okay. See, in fact, taking another tests actually updates your belief in the hypothesis. Okay? Bayes' rule is a tool to use several times in order to update your belief. For frequency type probability, it's just a math result. However, Bayes' rule is central for applications of personal probability. It offers a way to represent rational change in belief in the light of new evidence, says Professor Hacking. Of course, the entire idea has its own challenges, such as how to come up with the prior probabilities. Sometimes it's very common that you are not able to calculate to make a exact measurement about the prior probabilities. Sometimes it seems just a guess, you know. There's another issue called the requirement of the total evidence, and some authors had been more concerned about, and others hadn't because uh, their inductive logic systems don't have this issue, you know. But of course, there are another problems to solve on the field, okay? Well, to sum up, coherence is to avoid a shear loss contract. Coherence can allow us to use Bayes' rule with belief type probabilities. Bayes' rule is a good tool to update our beliefs and suggests a way to start doing inductive logic. Well, for your attention, thank you very much. Bye bye.